Hi everyone. This again is a lecture in continuation with the series of lectures I've been posting on the problems on sequential systems. I thought it may also be useful for those of you who are preparing for exams like GATE and so on. And some of these results are good to know. Okay, so here the problem is you're supposed to find out the integrals of two functions shown here. Okay, so this is definite integrals, integral minus infinity to infinity of sine 80 by 80. What is the value of that integral? And the second integral that you are supposed to find out is a squared value of the same function. It says sine 80 by 80 magnitude squared dt. What will be the value of this integral? Now, if I have to compute this integral in time domain, it's going to be a very tedious task. Okay, it may not even be very easily doable, or you may have to use some interesting mathematical ideas to solve problems like this. But this integral can actually be solved extremely simply by using properties of Fourier transforms. And one such property which we are going to use is what we call the duality property or symmetry property. Now, sinc functions are functions that we very commonly encounter in signal processing. I mean, whether it's in RF systems or digital communications, we encounter these functions of this type, sinc, sin x by x, very commonly. Okay, so very briefly, I'll talk about the sinc function. Sinc function happens to be the Fourier transform of a pulse function. So if you take a pulse function whose pulse width is t seconds, which is what is shown here, it's a symmetric pulse function whose center is at the origin and whose pulse width is t seconds. I'm going to represent it as pt of t. So this simply means it's a pulse function with unit amplitude. The amplitude of this pulse function is unity, and the value at t equal to 0 is 1, and the width of the pulse is t seconds. Now, one can use some mathematics to calculate the Fourier transform. I'll directly quote the final result. The Fourier transform of the sinc function, of a pulse function, happens to be a sinc function. It's nothing but a sinusoid, sin x, multiplied by 1 by x. 1 by x is a hyperbolic function, and you're multiplying this with a sinusoidal function. So, if you plot it, if you try to graph it, it will be just like a sinusoid, but its amplitude will keep decaying as you move away from the origin. Okay, so that's what you see here, and the decay of this amplitude will be as 1 over f. Okay, so that's the sinc function. Now, sinc function, if I try to find its squared value, squared magnitude integral of its squared magnitude, it will be finite. For a sinusoid, it's not finite, but if I multiply it by 1 by x, because I'm multiplying it by a decaying function, the squared integral. So what I mean by that is, let x of f be this function, mod of x of f square df. If I integrate it for all free f, the variable f here is frequency, this is going to be finite. Okay, this is not finite for a periodic signal like a sin x function, which is a sinusoid. A sin of x, it's not finite. Because I'm multiplying it by 1 by x, okay, it's going to decay down as you keep increasing x. Its values, the word that we are going to use is square integrable. Okay, if you square the function and integrate it, it's going to give a finite value. Some very simple things that you have to understand for the sinc function, or if you take a pulse function of width t seconds, then in frequency domain, you will have zeros of the sinc function at 1 by t, integral multiples of 1 by t. Okay, so that's one thing. If the width is t seconds, in frequency domain, it will be a sinc function, which is a sin x by x, and it will have zeros at multiples of 1 by t. Okay, and most of its energy of this function will be concentrated within this interval minus 1 by t to plus 1 by t. Okay, what is the exact value? You have to calculate it numerically. Okay, so this is something a very interesting fact that we use in digital communication systems. Okay, because we know that even though the frequency spread of this signal is infinity, we know most of its energy is contained within a certain band of frequencies, which is normally used to define bandwidth. Okay, so most signals don't have a clear, precise definition of bandwidth because they tend to extend for all values of frequency. But we try to see in which region most of its energy is concentrated, and there are different, probably when I talk about this course on signals and systems, I'll define those definitions of bandwidth. Okay, how do we define bandwidth for a signal which extends all the way till infinity in the frequency domain? So right now our focus is not that. Our focus is just to think a pulse function is going to have a Fourier transform which will look like a sinc function, and the zeros of the sinc function will be at integral multiples of 1 by t. The exact function for the Fourier transform of a pulse function is t sinc pi of t, where sinc of x is defined as sin x by x. So usually some textbooks use sin pi x by pi x, some textbooks use sin x by x. So generally what I do is when I write a sinc, I usually write the definition of sinc function as well. So when I'm posing questions in exams or setting assignments in my courses, I usually give the definition of sinc function beside the sinc. Okay, wherever I'm writing this function. Now, if you look at this function here, some simple things to read from this function is the average value which is defined as x of 0. So if you take the Fourier transform of x of 0 is the DC value of the Fourier transform, which is nothing but the average value of this function. So if you integrate it in time domain for all time, that gives you the average value, and that average value can be directly read from the Fourier transform by reading its value at x of 0. So that's something to keep in mind. Now what I'm going to do is, this is a result that we are going to keep in mind, which is if I have a signal, a pulse signal of width t seconds, pt of t, the Fourier transform is t into sinc pi of t. Okay, you can immediately see that sinc pi of t is sin pi of t, and sine function has zeros at n pi, so pi of t equals n pi, so which means your f equals n by t. So your zeros for this function will be at these values, where n equals 0, 1, n equal to 1, 2, 3, 4, and so on. At n equal to 0, what happens is you get a 0 by 0 form, and we can very easily see that sin x for small values of x can be approximated to x. So sin x divided by x will be approximately equal to 1, right? So the numerator is x and they both cancel out for small values of x. So it converges, the ratio converges to a value which is equal to 1, and it's non-zero at f equal to 0, or x equal to 0 in this case. So all the zeros occur at n by t. So we'll just keep this result in mind and apply the duality property. What does duality property say? Again, which is something which can be very easily proven, but right now I'll just quote the final result. If x of t is a time domain signal with a Fourier transform x of f, then capital of x of f, just replace f with t, okay, we'll have a Fourier transform of x of minus f. Okay, so if x of t happens to be an even function, which is the case here, even function means the function is symmetric around the origin, then x of minus f will also be equal to x of f. So this is what we are going to use. If I have a pulse function of width t seconds, I can write pt of t is t sinc pi of t. So now I'll take this function t sinc pi of t and just replace t by b. B is just a variable. Instead of t, I'm just using a different variable b here. So b sinc pi t b, instead of f, I've replaced it with t. We'll have a Fourier transform of pb of minus f. Okay, whatever is present here, that will be the pulse width in frequency domain. So here it's a sinc function. So whatever is present here, pi t b, that b here will be the width of this pulse in frequency domain. pb of minus f is also pb of f. So in frequency domain, it's going to look like this. B sin pi tb by pi tb will have a Fourier transform of a pulse function whose amplitude is 1 and pulse width will be b. Okay, now B here happens to be units in hertz. Now, but if you look at this function, we are interested in finding sine 80 by 80. It should be like sinc function. So what I'll do, I'll just multiply the function by 1 by b. If you multiply a function by some constant in time domain, Fourier transform also gets multiplied by the same value. So if I multiply it by 1 by b, I have to multiply the Fourier transform also by 1 by b. So the Fourier transform of sine pi t b by pi t b is 1 by b times a pulse function in PB of f is a pulse function with unit amplitude and a pulse width of b hertz. So that's it. Once you know this result, immediately you can just put pi b equal to a, because we are supposed to find out sine 80 by 80. It should be in this format. So if you just call pi b equal to a, then I'm going to call this function x of t, which is sine 80 by t, 80. We'll have a Fourier transform of, so it will be instead of 1 by b, b here is a by pi. So 1 by b will be pi by a times p a by p into f, p a by pi of f. So the pulse width in frequency domain will be a by pi hertz. So I've drawn this function, sketched this function in frequency domain. You can see the amplitude is pi by a here. That comes from this, it's 1 by b, which is nothing but pi by a in our example. And the pulse width is a by pi. That's it. The moment you know, you can just relate this function to a very much simpler function in frequency domain. This problem is very trivial to solve. The first step, you're supposed to find out the average value of this function. That's if you integrate this function, what happens, what do you get? That is simply x of 0. You just have to read the value of the Fourier transform at the origin, which is pi by a. So the value of this integral is simply pi by a. I can directly read it from the Fourier transform of the signal. The next part is the squared integral. So if I square this function and integrate in time domain, now I'll use something called Parseval's theorem. Again, for those of you who have taken a course on signal systems, it's very simple. I'll discuss this when I take the course. It's a very powerful and useful theorem, which says that if you want to find the energy of a signal in time domain, you can just find the energy of the signal, of the Fourier transform of the signal, and that will exactly be the same. If I square integrate the function in time domain, that will exactly be equal to the square integrable value in its value in frequency domain. And to square integrate, I just have to square this function. Pi by a becomes pi by a whole square and integrate this. It's a simple rectangle. So amplitude is pi by a the whole square, and base, it's length into breadth. So I can just treat this as length and this as breadth. Your breadth is pi by a the whole square. Length is a by pi, right? So then multiply the two, you get pi by a. That's it. So the value of this squared integral, okay, happens to be pi by a. So here I think I made a small yeah, so there is no issues here. So yeah, so the value of the squared integral is also pi by a. Okay, so that's it. So we have used the properties of Fourier transform to solve this very simple problem, which is I've tried to find out the area of a function, which is very difficult to compute it in one domain, which is time domain in this case. I just had to transfer it to frequency domain. The problem became much simpler. That shows you the power of Fourier transform. The properties of Fourier transforms can be greatly useful in solving very complex mathematical problems. I'll discuss more such examples and at a later stage, and probably when we go to the course, I'll talk in much greater detail. Thank you.